Hello everyone, I am Deepthiruk Maji, a PhD student at the University of Massachusetts Amherst, and today I am going to present our work DACF, which is a system for day-ahead carbon intensity forecasting of power grids using machine learning. This work has been jointly done with my advisors Ramesh Sitaraman and Prashant Shenoy at the University of Massachusetts Amherst. First, let me start by defining carbon intensity. So carbon intensity is the carbon emitted in grams per unit of electricity produced or consumed. Generally, each region has a mixture of sources producing electricity. So if you look to the left on the pie chart, we can see the sources producing electricity in California, as well as the fraction of electricity produced by each source. Now, these sources are both renewable like solar and wind, as well as non-renewable like natural gas and coal. And each source has a carbon emission rate associated with it. The carbon emission rate is the amount of carbon emitted by a particular source when it's converted to 1 unit of electricity. The carbon emission rate of non-renewable sources like natural gas is higher than that of renewable sources like solar or wind. So mathematically, we can define the average carbon intensity as the weighted average of the fraction of electricity produced by source I multiplied by its carbon emission rate. The average carbon intensity is an indicator of how green the source mix is and how green the electricity produced on average is for a particular region. The lower the value of the average carbon intensity, the greener is the source mix and the greener is the electricity produced on average for that region. However, this value is not fixed and it varies across region and across time. So if we look on the left, we can see three regions, and Texas has a high dependency on fossil fuels for producing electricity. As a result, its average carbon intensity value is high, whereas Sweden relies heavily on renewables and consequently has a much lower carbon intensity value. Not only across regions, but even within a region, carbon intensity varies across time. So if we look on the plot on the right, we see how carbon intensity varies throughout a day in California. During daytime, due to abundant solar energy, the carbon intensity values are lower. However, in the evening, most of the electricity demand is met by sources like natural gas, and hence the average carbon intensity value goes up. Thus, carbon intensity varies both across time and across regions. But why do we need carbon intensity forecasts? So, as the grid is beginning its transition to a low carbon future, many carbon optimization solutions are emerging, which shift energy from high carbon region and time to a low carbon region and time. Since we know that carbon intensity varies across space and time, if we can forecast where and when the carbon intensity value will be less, we can reduce the overall carbon emissions. Let's take an example. So let's say we have a system which has data centers in two geographically distributed regions, and we are able to forecast that one region will have lower carbon intensity values in the near future. Then we can configure our system in such a way that it routes more client requests to the low carbon region and hence reduces the overall carbon emissions. So carbon optimization solutions like these need accurate carbon intensity forecasts, and hence this carbon intensity forecasting is an important problem to solve. Formally, we can define the problem statement as follows. We take an input the historical electricity production data by all the sources in a particular region. We take in input the carbon emission rate of each source, and we also consider the weather forecasts. So we consider weather forecasts because they directly affect renewable energy generation. So for example, if we know that tomorrow is going to be cloudy, we can expect that the electricity generated from solar energy will be less tomorrow, and this in turn will affect tomorrow's carbon intensity. So we take all these as inputs and then we output accurate hourly carbon intensity forecasts. In this paper, we only talk about day ahead, that is carbon intensity forecast for the next 24 hours. Now, there are already some solutions existing in the market today. However, each has their own problems. So solutions like electricity map provide both real-time as well as carbon intensity forecasts. However, both their model and their data are proprietary, and hence to availing the service is expensive for most consumers and researchers. National Grid ESO provides free carbon intensity APIs. However, they're only constrained to the UK region. Other earlier works consider only historical data while predicting carbon intensity and ignore important factors like weather forecasts. Consequently, they have higher prediction errors. To overcome all these challenges, we present our solution, DACF, which is a system for day-ahead carbon intensity forecasting. DACF uses future knowledge like weather forecast and source production forecast to get the carbon intensity forecast. By source production forecast, we mean the predicted day-ahead electricity produced by a particular source. DACF has a general framework and a plug-and-play architecture, which makes it applicable to any region throughout the world. DACF is also accurate and robust. We tested it in 6 regions across the US and the Europe, and DACF provided accurate carbon intensity forecast, and the system is also robust. Also, all the models and datasets used in DACF are publicly available and is easily accessible in the following GitHub repository. And so it can be accessed easily by researchers and consumers for their work purposes. So now coming to the DACF architecture, the key idea behind DACF is simple. We know that carbon intensity is just the weighted average of the fraction of electricity produced by a particular source multiplied by its carbon emission rate. So if we can predict the fraction of electricity produced by each source, we can predict carbon intensity using a similar formula where the forecasted carbon intensity now becomes the weighted average of the fraction of electricity or the predicted fraction of electricity produced by each source multiplied by its carbon emission rate. To that end, we employ ANN models to get the source production forecast. So for each source, we input the electricity produced by each source and output the source production forecast. For renewable sources like solar, wind, and hydroelectricity, we also include weather forecasts as additional features. Once all the source production forecasts are obtained, we simply use the carbon intensity forecast formula to get the day-ahead carbon intensity forecast. DACF has a general framework in the sense that it does not matter what sources are producing electricity in a region, since we have separate ANN models for each sources. Also, we keep the model hyperparameters same, and although we have to retrain ANN for each region, retrain the ANN models for each region, since the fraction of electricity produced by different sources vary across regions, we keep the model hyperparameters as well as the type of features same across all the regions. DACF also has a plug-and-play architecture in the sense that if there is a better source production forecasting model available somewhere, we can integrate it seamlessly into DACF. For example, if there is a better wind forecasting model available somewhere, we can replace our ANN model with that better model while keeping the remaining architecture as it is and seamlessly improve the DACF performance. This plug-and-play architecture, as well as the general framework, makes DACF applicable to any region throughout the world. Now, talking about evaluation part, first, we checked how DACF performed across geographically distributed regions. So on the left, we can see a 3-day time series in California, and we see that the predicted values of DACF matches the general pattern of the actual carbon intensity values and is able to match the unpredictability in the time series. Quantitatively, we see that we measured DACF performance in terms of MAP And we see that DACF performance is 6.4% MAP on average across regions, and with an worst case MAP of 9.08%. Thus, DACF provides accurate carbon intensity forecast and is also robust across geographically distributed regions. Next, we compare DACF with the current state of the art in terms of MAP, where the lesser value is the better. And we see that DACF outperforms the current state of the art by achieving an average MAP decrease of 6.4% and a maximum MAP decrease of 8.6% across the tested regions. So we have shown only 3 regions here. However, we have tested in 6 regions. And for further details, please refer to our paper. Thus, to sum up, in this, so we present DACF, which is a general framework for forecasting day-ahead average carbon intensity in the power grids. DACF provide accurate forecasts and is robust across geographically distributed regions. It also outperforms the current state of the art by 6.4% on average. And as a future work, we want to go beyond the prediction period of 24 hours and provide multi-day forecasts so that even more carbon optimization solutions can incorporate DACF into them. And finally, we have open sourced DACF, and it is easily accessible and publicly available in the following GitHub repository. So we request all of you to please use DACF and provide us your valuable feedback so that we can improve DACF further. Thank you, and I'll be available in answering any questions that you may have.